In this video, we're going to extend ourselves a little bit from what we've seen already, and we're going to look at relations in several variables, and that's to contrast with functions. The idea with a function is if we have a single input, we get a single output. Relations, there might not be that one-to-one relationship. As a quick element of terminology, when we talk about points on the real line, and we can only go left to right, we call that R1 or R, the set of real numbers. Points on the plane, X against Y, any point in that set belongs to R2. And if we go in 3 dimensions, X, Y, and Z, then we would be talking about points that belong to R3 or 3-dimensional space. Now, some of the shapes that we see in R2 and R3, 2 dimensions or 3 dimensions, are best described by relationships. For example, if we're in 2 dimensions, just the X and Y axes, and we're confronted with the equation x squared plus y squared equals 25, first of all, that defines a set of xy values. And that's essentially equivalent to a graph. And if we remember back earlier in the course, what this defines is the circle with radius squared, x squared plus y squared equals radius squared. So a radius of 5 around the origin, every point being exactly 5 away from the origin here, and we can see the Pythagoras hiding in that by drawing the triangle that comes out of here. X is the distance from the origin to our point horizontally, y is the distance vertically to our point, and so x squared plus y squared equals the hypotenuse squared 5. That would describe any point at all on the circle. We also remember that we can tweak that by putting some values, addition or subtraction, inside the squares. So if we look at the graph of, let's take a step back. Oh my God, wrong line. So if we take a look at this graph, what we're measuring is the distance between some point x and the point 2. That's another way to remember that difference between x and 2. Well, that means that we're essentially centering at x equals 2 and measuring how far away on either side of that we are. Same thing for this. This is the distance between a y value and, well, this is minus 1. So minus 1 for the y value. So what we would be describing here is a circle. We measure the x away from 2. That's x minus 2. We measure the y distance, which is y plus 1, or y minus 1. And the hypotenuse we get back is going to be 5 for this. That'll be hypotenuse squared. And that gives us a circle again, not quite to scale here, but a circle with radius 5, and the center is at the point 2, -1 in x and y. Now the fun part comes in when we go to 3 dimensions. If we imagine our regular x, y, z axes in 3 dimensions, and we look at our expression here for x squared plus y squared plus z squared equals 25, it should not be a huge shock to realize that this describes a sphere. And the radius again is going to be the square root of 25 or a radius of 5. So that would look like this sketched out on the 3-dimensional axes x, y, and z. Now what makes a sphere? It's the fact that every point on it has the common distance to the origin. And what that is here is the distance squared. This 25 represents the distance to the origin squared, from which we can reverse engineer a formula. If we want to pick any point x, y, z to the origin, well, we just look at our x distance, our y distance, and our z distance. The direct line, straight arrow distance back to the origin is going to be squared, is going to be x squared plus y squared plus z squared. Or if we want to rearrange that a little bit, the distance is the square root of x squared plus y squared plus z squared. And notice this is also the magnitude of a vector. If we had a vector that was going out to this point, we would get its magnitude by adding up the components all each squared and then taking the square root at the end. So there's nice tie-ins to some of the earlier work we've done with three-dimensional points and vectors. We can take this in a couple of other different directions now. If we want a formula for a sphere with radius 5 and centered at 2, 4, -1, we already have some essential ingredients here. It's going to be something with x squared, something with y squared, and something with z squared equals 5 squared. That's modeling off of our canonical example here where the center's at the origin. But if we're centered at 2, we can use the rationale we used earlier and say we want to measure the distance between x and 2. We capture that with an x minus 2. We want to measure the distance between our point and 4 in the y direction. That distance is going to be literally the subtraction or the difference between y and 4. And last but not least, the distance between -1 and our z coordinate is going to be z minus -1, which if you like, you can certainly rewrite as z plus 1. So by extending our work with circles, where we simply had the x and y components equals r squared, we can extend that to three-dimensional surfaces and three-dimensional analogs of circles, which are spheres, with not really any fundamental change in the formulas. We're just adding that z component to the distance calculations. We can also extend our earlier distance formula here to apply to a distance not between just a point x, y, z and the origin, but x, y, z and some other point, let's call it ABC. So if we have our x, y, z point, and we have our ABC point, then what we would measure is how far they are in x, how far they are in y, and then how far they are in z. Well, each of those ingredients is x minus a, how far are the two components in x, y minus b, how far are the two components in y, and z minus c, all of those squared and then square rooted to get our distance. So again, we see here this nice tight relationship between the form of equations for spheres and the not unsurprising connection to the formula for distances. And the relation comes obviously from the fact that spheres describe points that all have the same distance from a center. So we have a natural relationship to the formula for distances in general. And what we've seen is very simple analogs of what we have in 2 dimensions with formulas for circles at different centers and different radii, and the natural extension of those to spheres in 3 dimensions.